welcome. Uh, so, in the last lecture we have started discussing about an arbitrary finite abelian group and to do Fourier analysis on that. And so, what we have seen is that let G be finite abelian group and we have defined G hat to be the set of all characters on G, that is a map from G to C such that gamma of x plus y, where plus is the group operation on G, is equal to, rather we have taken it to the unit circle gamma of x, gamma of y, this for all x y. So, what so this is the basic ingredient to do Fourier analysis. So, for example, if we have taken Z n, then we know that these gammas were given as the root nth roots of unity, and then we have developed the Fourier analysis and finally got the inversion and the Perceval formula for this. So, now and we have seen that apart from Z n, Z square Z star q is also a finite abelian group, which consists of all the unit element of Z q, and so we can do in general for any arbitrary finite abelian group. Okay. So, now let us take define C G to be the set of functions on G f a function, the set of all function. Then we have seen that C G is a vector space and the dimension of C G is the cardinality of G. This is the number of elements in the group G. Okay. So, this as just like before, you take the evaluation function delta I of x, the bases are very clearly you can write that let x 1 to x n, they are the elements in G, it is a finite elements, and you define delta I of x is equal to 1 if x equal to x I 0 otherwise, then that is going to give you a basis for C G. So, recall that to do Fourier analysis we had defined an inner product in the space of all functions on Z n, and in that direction let us just make the notation for inner product. Let f g belongs to C G, then define the inner product exactly as in Z n. So, this is equal to 1 over n, summation over x varies over G, and then this is f x g x bar. And another fundamental thing what we do is that f convolution of G of x, this is defined to be 1 over n summation over x varies over G, and f of x minus of y G of y, which is equal to also, if I make a change of variable, sorry, here it is y belongs to G f of y g of x minus of y. This is also because we are taking this as an abelian group, this is this. Okay. So, so one of the, if we want to have an analogy with what we have done in the for the 2 pi periodic function and Zn. So, what we would like to have the characters there, they form an orthogonal set, that they are mutually orthogonal. So, here we would also like to see that whether that holds in this setting or not. So, now towards that, and what we need this lemma. So, uh, now throughout this we will denote gamma 0 to be the trivial character. That means, gamma 0 is a function from g to t, which is defined as 1. So, that is the, we will call it as the trivial character. Gamma 0 is always identically equal to 1. Now, suppose gamma belongs to g hat and gamma is not equal to gamma 0, then summation over x varies over g gamma of x, this is equal to 0. So, there it was easy because we know exactly what the form of in Zn form of the characters are. Then if you add all the nth roots of unity, then we can get 0. And in this case, because gamma is not the trivial character, therefore, there exists a x belongs to g, or rather x naught belongs to g, such that gamma of x naught is not equal to 1. Otherwise, if it is 1 for every x belongs to g, it is going to be the trivial character. So, then gamma of x naught summation over x varies over g gamma of x, this becomes x belongs to g gamma of x naught gamma of x. Now, this by our definition the gamma is a character, therefore, this is x plus x naught. Now, if I make a change of variable, this again I will be in g, this is over all elements in g gamma of y. So, now this will implies that 1 minus gamma of x naught into summation over x varies over g gamma of x, this is equal to 0. Now, gamma of x naught is not equal to 1, therefore, this will imply that summation over x varies over g gamma of x, this is equal to 0. Okay. So, that is this will be a very useful observation. Then we get into our orthogonality, what we are asking for. Let gamma 1, gamma 2 belongs to g hat. The g hat is the dual of g, set of all characters of g, then inner product of gamma 1, gamma 2, this is equal to 0 if gamma 1 is not equal to gamma 2, is equal to 1 if uh, gamma 1 is equal to gamma 2. So, the proof is easy, gamma 1 gamma 2, this is 1 over n summation over x varies over g gamma 1 of x gamma 2 x bar. This by definition is 1 over n summation over x varies over g gamma 1 of x, and the character gamma 2 bar is the character what we have defined, that gamma bar of x equal to gamma x whole bar, and we have seen that that is the character for g. So, this is a pointwise multiplication, therefore, this is x belongs to g, this is gamma 1 gamma 2 bar of x. Now, gamma is not equal to gamma 1 is not equal to gamma 2, therefore, gamma 1 and gamma 2 bar, they are not trivial character. This character is because gamma 1 is not equal to gamma 2. Now, this is going to be 0. Now, if gamma 1 is equal to gamma 2, this is by a previous lemma, gamma 1 is equal to gamma 2, we get that this is x belongs to g mod of gamma 1 of x square, and that is nothing but 1 mod gamma. So, n times of that, this is equal to 1. So, they are orthonormal. Now, the question comes that whether in that case what we have seen is that all these characters they form an orthonormal basis for the corresponding vector space of functions over Z n. Now, this it is natural to ask that whether all these characters they will form an orthonormal basis for C g or not. Now, in order to have the basis, so now does is that first we need to check that whether they are linearly independent or not. So, now first of all, how many characters can there be in G for any arbitrary finite abelian group? There we know that in Z n it is exactly n. Now, what about here? So, what we have observed is that you take any x, let x belongs to G, and cardinality of G is equal to n, the number of elements, then x to the power n is equal to the identity element in G. Therefore, gamma x to the power n, this is equal to gamma x n, which is equal to gamma of E, which is equal to 1. Therefore, they are the all these characters, they are nth root of unity. Therefore, the number of element in G hat is less or equal to the number of element in G. We do not know whether they are precisely equal to the number of element in G. So, nevertheless, they are finite in number. So, what we can see about the linear independence. So, let summation over j, j is some finite set, alpha j gamma j, where gamma j's are zeros, gamma j contained in G hat. Then what we take is that summation over j belongs to some finite set alpha j of gamma j, and I take the inner product with some gamma k. Then this is nothing but alpha k by the orthogonality relation. So, now this is 0. So, therefore, each of these alpha k 0, therefore, gamma j is linearly independent. independent. Okay. So, now one would ask that are they exactly equal to n? In that case, what we know is that if there are exactly n number of elements in G hat, and we know that they are linearly independent in C G, and the dimension of C G is n. Therefore, G hat is going to span and they will be the orthonormal basis for C G. So, this theorem has this result has several proofs. So, we will prove it with basic linear algebra technique. So, let us for that let V be a finite dimensional inner product space. Let us say with dimension D, and the inner product is given, we will denote it by this. Okay. So, you take a linear map, a linear transformation T from V to V is said to be unitary if T V W T V T W is equal to V W. So, this we have studied in our linear algebra course, that the spectral theorem for unitary operator says that T is diagonalizable. By spectral theorem, T is diagonalizable. What does that mean? That is, there exist eigenvector V 1 to V d of T such that V is equal to span of V 1 to V d. So, we will get a basis element for V consisting of the eigenvectors of T. So, now suppose T 1 and T 2 are two unitary transformation on V, then obviously one can get a basis element consisting of the eigenvectors of T 1, and also one can get basis element consisting of the eigenvector T 2. Now, the natural question is, does there exist a basis V 1 to V d such that VI's are eigenvector for both T1 and T2. That, in other words, is can T1 and T2 be simultaneously diagonalizable? In other words, can T1 and T2 be simultaneously diagonalizable? So, that is what one need to check. So, this is a natural question. So, now let us see what are the conditions we would like to impose such that we can get the simultaneous diagonalizable of T1 and T2. So, since T2 is unitary, hence diagonalizable, there exist V1 to Vd basis such that T2 of Vi is equal to, let us say, beta I Vi, where beta I has the eigenvalues. Okay. So, therefore, I can write V as the direct sum of the subspaces V of, let us say, beta 1 direct sum of B of beta d, where V beta 1 is nothing but the span of V beta I, this is nothing but the span of V I. The V I is the one dimensional subspace of V, and because they are the basis element. So, therefore, I can have a direct sum decomposition. So, now let us see the action on of T beta 1 T 1 on all these subspaces. Now, for if T 1 of V beta I is contained in V beta I, if this is, we are assuming that it is if, then T 1 is unitary on V beta I for each I. To be more specifically, T 1 restricted to V beta I, this is unitary on V beta I. Now, if it is unitary on V beta I, therefore, it will be diagonalizable. Now, once it is diagonalizable, there exists W I belongs to V beta I such that T 1 W I is equal to some alpha I omega W I. So, therefore, T 1 of V I, this is equal to, and by the way, this W I is nothing but some R I V I, because W I belongs to V beta I, which is one dimensional subspace. So, this is equal to T 1 of 1 by r I w I, which is nothing but 1 by r I, you take it out, T 1 of w I, which is equal to 1 by r I alpha I w I, and we know that this is equal to alpha I V I. So, now V I is also an eigen value, a eigen vector for T 1. V I is an eigen vector for T 1. So, obviously, they have the common eigen values if this condition holds. Now, when does this condition hold? Now, if I want to show that V beta I are invariant under T 1, then I need to show that I take any element V on V beta I to prove star we need to show if V belongs to V beta I, then T 1 of V also belongs to V beta I, that means it is going to be an eigen vector for T 2, then T 2 must be equal to some beta I T 1 of V. If we can show that, then star will be true. Now let us add T 2 of T 1 of V. Now, suppose if we have a condition, if we put here that T 1 and T 2 commute with each other, then this I can pull it out T 1 T 2 of V. Now, this is nothing but beta I of some beta of V, because V is an eigenvector. So, this is, so then T 1 V is an eigenvector. So, therefore, it suggests that if T 1 and T 2 are two unitary operators on V, and so hence what we get T 1 T 2 unitary on an inner product space V, and if T 1 T 2 is equal to T 2 T 1, then T 1 and T 2 are simultaneously diagonalizable. This suggests to ask that what about if I have a n tuple of unitary operator on V on an inner product space V, then if they commute with each other, then can they be simultaneously diagonalizable. So, in fact, that is going to be true, and in the next lecture we will see the proof. The proof will be by induction. Thank you.